In this video, we shall look at a few review problems associated with electric potential. Problem 1. What potential difference is needed to stop a proton having an initial speed of 4 times 10 to the power 5 meter per second? Let's assume the region where this potential difference exists is represented by these two lines. So the left-hand side is where the potential is negative and the right-hand side is where the potential is positive. So it creates a potential difference. Let's call it delta V. So a proton enters this region with an initial speed given there. So let's call that initial speed U. By the time it gets to this region, it is completely at rest. So over here, the speed of the proton is 0 meter per second. Now we note the charge of the proton is given by 1.602 times 10 to the power minus 19 coulomb. The mass of the proton is taken to be 1.67 times 10 to the power minus 27 kg. So what happens is that as soon as the proton enters the region where the potential difference exists, it will be attracted by the negative potential and it will be repelled by the positive potential. So the potential difference would try to make the proton to go leftward, but because the proton has an initial speed, it carries an initial momentum to the right until sufficient effect of the potential difference kicks in to stop it completely, namely at that point. So if that's the case, what this number should be? We can use the conservation of energy. The initial potential energy, initial point is that point, plus the initial kinetic energy, the kinetic energy of this proton at that point, must be the same as the final potential energy plus the final kinetic energy, namely the final potential energy here and the kinetic energy there. Let's rearrange this equation a little bit. Ki minus Kf equals Uf minus Ui. So Ki is the kinetic energy of the proton when it is at the negative region. So that's given by half times the mass is that number, times the initial speed squared. The speed at that point is 4 times 10 to the power 5, square that. Kf is the kinetic energy of the proton here, and it's 0, so that goes away, minus 0, equals the difference in the potential energy between that point and that point, and that is given by the charge of the proton times the potential difference, delta V. We get that from QV final minus QV initial. The potential at the final location, namely here, is greater than the potential there. So this is a positive number. Putting in all the numbers, we can compute delta V. It is quite simply half times the mass of the proton, which is 1.67 times 10 to the power minus 27, times the square of the speed, 4 times 10 to the power 5 squared, divide by the charge of the proton, which is 1.602 times 10 to the power minus 19 coulomb. And that's going to give you 834 volts. And that's the answer. Problem 2. Find the electric potential at a distance 1 cm from a proton. What is the potential difference between 2 points that are 1 cm and 2 cm from a proton? Then repeat it for an electron. So part A, if you have a proton here, the potential it creates at a distance r, say there, is given by the following expression. The potential there equals K, where K is the constant, 9 times 10 to the power 9 in SI units, times the charge of the proton over that distance. K is 9 times 10 to the power 9. the charge of the proton is 1.602 times 10 to the power minus 19 Coulomb. The R here is 1 cm, so 0.01, and that's going to give you positive 1.44 times 10 to the power minus 7 volts. We note here that proton is a positive charge, so potential it creates will be a positive number. Now part B, let's assume that you have another point, let's say over there, and the distance is 2 cm. So what is the potential difference between this point and that point? Let's assume this point is point A and this point is point B. So let's assume we want to find VB minus VA. Now VB can be computed in a similar manner as in part A. It is K, the charge of the proton, over 2 cm, so 0.02 meter, minus KQ over 0.01. 1 cm converted into meter. Substituting the values of K and the charge of the proton, we get the following number for the potential difference of VB minus VA. It's minus 7.21 times 10 to the power minus 8 volts. Now let's do part C. Repeat the calculations for electron. If we substitute this charge with an electron, the only difference in the calculation is that this number here now will become a negative number because the charge of an electron is minus 1.602 times 10 to the power minus 19 Coulomb. So simply putting the minus sign there, the answer will become minus 1.44 times 10 to the power minus 7 volt for the potential that electron creates at 1 cm distance from it. Likewise, to calculate the potential difference between the 2 points for an electron, you put a minus sign here and you put a minus sign there. So this minus will make this minus a plus, like that. And the overall answer will become plus 7.21 times 10 to the power minus 8 volts for the potential difference. And that solves the problem. Problem 3. A wire having a uniform linear charge density mu is bent into a shape shown in figure below. Find the electric potential at that point, the center of that semicircle. Let's divide the calculation into 3 parts. The first part is the left-hand side of that wire. The second part is the right-hand side of that wire. And the third part is that semicircle part of that wire. Let's do the left-hand side first. Let's divide up this entire left-hand side segment into a very tiny segment which contains a charge, say, dq. And the length of that element, let's call it dx. Let's align this linear segment of the wire along the x-axis, like that. So the potential that this dq, only dq, produces at the origin here is given by the following expression. Let's call that potential dV. And that equals to k, the constant, 9 times 10 to the power 9, times the charge that element contains over this entire distance. So since the origin is here, the location of that element is, let's call it, minus x. So over minus x. So that is the magnitude of the distance, x. I'm choosing the negative sign here because that point is on the left-hand side of the origin. One other thing that we have to be aware of is dq can be expressed in terms of that linear charge density. Linear charge density measures how much charge is contained within a specific length. So in that length, dx, the amount of charge dq, is quite simply mu times dx. So we can write that dq as quite simply mu dx. In order to determine the total potential that this entire segment creates at the origin, we need to integrate the above result with respect to x. So it's going to be minus k mu. K and mu are constants, so you can take that out, dx over x. As you move from here to there, the limit of integration, namely the lower limit and upper limit for x, will go from minus 3r, because this is r, this is 2r, so that point is minus 3r, all the way here, which is minus r. And this integral will be minus k mu natural log of r over 3r. So that's simply k mu natural log of 3. So we have a first contribution. VL is just k mu natural log of 3. Now let's do the right hand side. We can do the same trick. Let's divide up this right hand segment into small segment which contains charge dq. And that charge dq is at the distance x from the origin. The length of that element is, let's call it dx. The potential it creates at that origin is given by k dq over x. And expressing dq in terms of mu, it is just mu dx over x. And the overall potential is given by the integration of the above result dx over x. As you move the element from here to here, the limits of integration will become r for the lower limit and 3r for the upper limit. And that is just k mu natural log of 3. So we have obtained the second contribution, k mu natural log of 3. Now the semicircle part. Let's again divide up the semicircle into a very small element, and let's call that element as charge dq. So for that element, the potential it creates at that origin is k dq over the distance is just the radius of the semicircle, capital R. So the total potential that this entire semicircle produces at the origin is found by simply integrating the above expression. Now we take k out because it's a constant, and we take the capital R out because that is also a constant, namely the radius of that semicircle. The total charge that this semicircle contains is given by the linear charge density mu times the length of that semicircle, which is just pi times the radius of that semicircle. So substituting that in here, we get k over r mu pi r. So this r goes away and you get mu k pi for the third contribution. Adding the three contributions up, namely this, and that, we get the following for the total potential at point O created by this entire charge arrangement. It is k mu natural log of 3 plus another k mu natural log of 3, so that would make it 2 k mu natural log of 3 plus k mu pi, which is just k mu times 2 natural log of 3 plus pi volts. And that's the final answer, and that solves the problem. Thank you for watching.